Why don't I flinch? Because the laws of science differ fundamentally from all other. My face.
In this video, we're going to discuss power. Power is the rate at which work is done, or the rate at which energy is expended. So the word rate here simply means something is happening per second. In the case of power, it means work is being done per second. So the formula for power says power equals work done over time taken. P equals W over T. Okay, the units are joules per second. That is because we've got work. That is because we've got work on top and time at the bottom. So the units become joules per second. Okay. Now, 1 joule per second is equal to 1 watt. Okay. Now, the wattage of a machine tells us how much work per second the machine can do. You'll notice that many machines have got different power ratings. All right. For example, in this, we've got 3 cars: the BMW, the Mercedes-Benz, and the Audi. The BMW has got a power rating of 115 kilowatts, the Mercedes-Benz 125 kilowatts, the Audi 110 kilowatts. We're just focusing on the power, leave the other specifications of these cars. What we can get is that the BMW can do 115,000 joules per second of work. The Mercedes-Benz does 125,000 joules every second. The Audi, 110,000 joules per second, according to the power rating. So the wattage tells us how much work these machines can do. So if I, in theory, had a heavy trailer that I wanted to pull, which of these cars would probably do it better? Well, based on the power only, would probably go for the one with the higher power rating, okay? Assuming other factors are constant. Obviously, when it comes to cars, it's not always the power rating that you need to look at. There are a lot of other specifications that you also need to look at. But in terms of the power, the wattage of this car is higher than the other two, so it will do more work. Okay. Example 1, we've got a machine converts 300 joules of energy every half second. Can you calculate the power? Yes. Power equals work done over time. So we simply substitute 300 over 0.5. It will give you 600 watts. So this is a simple plug and play. Get the formula, substitute. A second example says a machine has a power rating of 1,500 watts. How long will the machine take to do 30,000 joules of work? How long means the time. So we want to calculate the time. So if we go to the power formula, P is equal to W over T, we can easily work out the T by substituting the values and solving for T. So 1,500 over 1 equals 30,000 over T. So here we do the cross multiplying technique, and then we discover that the T equals 30,000 over 1,500, which gives us 20 seconds. So it will take 20 seconds. Now, third example, we've got a block of 200 kg being lifted 15 meters vertically high in 25 seconds by a crane. What is the power developed by the crane? In this case, the work done is the work done in lifting the block 15 meters high. When we discussed work in one of our videos, we said if you lift an object vertically upwards, the work that you do is equal to the gain in potential energy, or simply mgh. So the work done here is the gain in potential energy of the object, all right, which is mgh. So in this case, it will be 200 times 9.8 times 15 divided by the 25 seconds. It gives you 1,176 watts. So when it comes to object moving vertically upwards and we are dealing with power, just beware that the work done by the machine in lifting the object up is equal to the gain in potential energy of the object. Sometimes an object is lifted up and then ejected at a certain speed. So some bore pumps are designed such that they can suck water from the bottom of a borehole and then eject it at a certain speed. Two amounts of work are going to be done in this particular case. The first amount is the W1 equals delta EP, the change in potential energy of the object. Well, when you change the vertical position of an object, one of the work that is done is the change in potential energy. The second work that will be done is delta EK. In other words, to change the speed of the object. We know that whenever you change the speed of an object, you need to do a certain amount of work. You need a net force to do that. And the net force will do work equal to delta EK. So the total work, or the work done by the pump or by the machine that does this, will be equal to W1 plus W2, which is delta EP plus delta EK, the same as delta Emac. So when it involves lifting an object up from the ground and eject it at a certain speed, the work done by the machine is going to be equal to the change in mechanical energy of the object. Right, let's use a free body diagram to try and explain this a little bit further. Suppose we are lifting an object vertically upwards and we're going to eject it at a certain speed. So the two forces that are in play are the force from the machine and the force of gravity. Now, we imagine that initially the object is at rest, and then it's going to have a final velocity of a certain value. Okay? Let's call that velocity, rather V. Okay? So which means there's a change from 0 to V. Because there's a change, we're going to have an acceleration. And once we have an acceleration, it means we have what? A net force. So there's a net force that causes this object to accelerate upwards. All right. So in terms of the net force, we know that the net force is going to be the force of the machine and the force of gravity. Now, since we're going upwards, we might as well make the upward positive and make the downward negative. All right. So the work done, the W net is going to be the net work done, is going to be the work done by the machine minus the work done by gravity. We are making an assumption that we're ignoring the effects of air resistance. So we're going to ignore air friction for this example. Otherwise, we'll need to factor in the force of friction, right? So this leaves us with delta EK equals work done by the machine minus delta EP. We know that because W net equals delta EK, we've talked about the work energy theorem. Work done by the gravitational force is equal to the change in potential energy of the object. So this simplifies to delta EK plus delta EP equals work done by the machine, which leaves us with the work done by machine equals delta Emac, because changing the kinetic energy, the sum of the kinetic energy and potential energy is equal to the mechanical energy of the object. Okay. Example 4. Calculate the power required to lift 200 kgs of water from a bowl that is 45 meters deep every minute and discharge it at 3 meters per second. So we now know that the total work done here is going to be the work done to lift the water and then to discharge it at 3 meters per second. Okay, so that is going to be the two amounts of work that are going to be done. All right, so the first one is delta EP, which means the final potential energy minus the initial potential energy. Whenever we use the symbol delta, it just means final minus initial. So it's 200 times 9,8 times 45 minus 0. This gives me a total of 88,200 joules. So to lift 200 kgs of water, 45 meters, you need 88,200 joules of energy. The next amount of work that will be done is to change the kinetic energy of the object. Okay? And this is 900 joules. So you'll need 900 joules to change the kinetic energy of 200 kgs of water. All right. So now I can go back to the power equation and say the total work done over the total time. We are told we need to lift this water up every minute. So every minute. So the rate here is every minute. That's the time that we're going to use. The time is the rate, which says every minute. Every minute is 60 seconds. And then we get 1,485 watts. So power equals work done over time. Sometimes the work done can be the change in mechanical energy of the object over the time taken to do that change. All right. What happens if you've got a constant force that acts on an object? We can modify the formula for power and come up with an interesting one. Let's start with the formula that says power equals work done over time. That leaves us with work done, force times displacement. Remember the work formula, when we spoke about work in one of our videos, we said work done is simply force times displacement. So as a result, power is now equal to force times displacement over time. We can actually simplify this to force times displacement over time like that. Okay? And then this simplifies to FV. So power equals force times velocity. So this formula is normally used when we're thinking of a constant force. When we're talking about an object, a constant force acting on an object, and usually the object moving also at constant velocity or speed. Okay, so power equals force times velocity. All right. Question 1. Now we've finished the basics of the introduction of the concept of power. Now we're beginning to do some practice questions. Now with those practice questions, it is a good idea if you can try to work the question by yourself and then check our answers, see if they're the same. Okay, try to work out the question by yourself and see if we get the same answer. A car of mass 2,000 kilograms travels at a constant velocity of 25 meters per second west. The total frictional force acting on the car is 1,000 newtons. Calculate the power developed by the engine of the car. So, we are told that the total frictional force that acts on the car is 1,000 newtons. But we are also told that the car is moving at a constant velocity. So this idea of the word constant velocity is important. It gives us a clue. Since the object is moving at a constant velocity, it means that the net force is going to be what? 0. There's going to be no net force that acts on the object. If there's no net force that acts on the object, well, the forces that are acting should be balanced. In this case, the horizontal forces are balanced. So the engine force and the frictional force produced a 0 resultant force. So which means that the engine force is equal to the frictional force. Okay? So if we were to make just a simple free body diagram here, we've seen that the car was going in that direction. That was the force of the engine. And in the opposite direction, we have the frictional force. So because there is no net force, it means these two are balanced forces. So if the forces are balanced, it means they're equal in magnitude, but are acting in the opposite direction. So we make an assumption. I always say make the direction of motion the positive direction. And this one is the negative direction. That's why you see in the calculation, I got the frictional force as a negative 1,000. Okay? Because it's acting in the negative direction to the direction of motion. All right. So now that I've got the engine force, I can easily calculate the power by saying power equals force times velocity. 1,000 times 25 gives me 25,000 watts. So the engine of the car must produce a power of 25,000 watts to keep this car moving at 25 meters per second west against a constant frictional force of 1000 newtons. Notice in this example, we did not need the mass of the car. Yeah, so guys, please learn to depict which information is relevant to the question. We did not need to use the mass of the car in this particular example. Okay. Question 2, we're told a combi of mass 2000 kgs approaches an incline at 72 kilometers per hour. The incline is 100 meters long and 20 meters high as shown below. Okay. The coefficient of kinetic friction between the wheels of the combi and the surface is 0.15. So, calculate the power developed by the engine. So the moment you see questions that give you information in kilometers per hour, we need to convert that quickly to meters per second. Okay, because we are always using meters per second. Our formulas are designed to use meters per second. So how do you convert from kilometers per hour to meters per second? Well, we say if you divide by 3.6, so you just say 72 divided by 3.6, this will give you 20. So this is actually 20 meters per second. Okay. Yeah. And then another clue, if you see a question that talks about the coefficient of kinetic friction, they give you the coefficient of kinetic friction. It means you're going to have to calculate the frictional force. They're just telling you that, oh, in this question, if you're going to need to use the frictional force somewhere in the calculation, you're going to have to calculate the frictional force yourself. All right, let's move. So, what's happening? We need to have an idea of the forces that are acting on this combi. So as the combi goes up the incline, what are the forces that act on it? The force of the engine, we can see, is going to be pushing the combi in the forward direction. Opposing that motion is the force of friction. We've also got the parallel component of the weight. Remember, the weight itself is acting in this direction. It's acting downwards. The gravitational force always acts vertically downwards, okay? But as the combi moves along the inclined plane, it is the parallel component of the weight that has the effect. All right. Now, we want to get the power developed here. So, how are we going to work that out? Is there a way of working out the work done? Or is there a way of working out the time it takes? So, our formulas for power are P equals W over T and P equals F times V. Because of this word constant speed, remember we've just talked about using this formula P equals force times velocity, especially when you see that word constant speed. Okay, but now, so let's have a go at this question. So we can use either of these two formulas, but let's see if we can use both of them. All right, so the first thing we're going to do, let's work out the angle of inclination. So the angle of inclination is 11,54. Sine theta equals opposite of hypotenuse. So this is the opposite side, that's the hypotenuse, and this angle becomes 11,54 degrees. We're going to need this, as you'll soon see later, we're going to need that angle there. Now, let's work out the normal force. Why do we need to work out the normal force? Well, because we need to calculate the frictional force. Okay? We need to be able to calculate these forces that are affecting the motion. Which are the forces that are affecting the motion? Well, we got three forces that are affecting the motion. We got three forces that are affecting the motion here. The first force that affects the motion is the FG parallel. The second force is frictional force. The third force is the engine force. So we need the magnitude of these three forces because they are affecting the motion of the object. Okay. So now we know what the normal force is. It's going to be 2,000 times 9,8, that's mg, times the cos of 11,54. It gives me 19,203,792 newtons. That's what normal force is. Now I can use this to calculate the frictional force. The frictional force is equal to the product of the coefficient of friction times the normal force. So in this case, the coefficient is given as 0,15. So which means the frictional force becomes 2,880,5688 newtons. So now I've got the frictional force done. Can I work out the FG parallel? Yes. FG parallel is equal to mg times the sine of theta. Okay? Remember when we spoke about objects moving on an inclined plane, there are two components of weight that you must always be ready to calculate. The parallel component and the perpendicular component. The perpendicular component is the mg cos theta. The parallel component will be mg sine theta. All right. So this becomes 2,000 times 9,8 times sine 11,54 gives us 3,921,09 newtons. So now we've got the force of the parallel component of the weight. We've got the frictional force. Can we work out the engine force? Yes, we can. Well, because we are told that this object moves at a constant speed. Constant speed means there is no acceleration, so the forces again are balanced. So we have a scenario where we've got balanced forces. The engine force acting in the positive direction is balanced by these two forces that are acting in the negative direction. Remember, you cannot have vectors acting in opposite directions and they're going in the same, having the same signs in your calculation. So the engine force is the sum of the frictional force plus the weight component. So this gives me a total of 6,801,5878 newtons. That's the total force from the engine required to maintain the constant speed of 72 kilometers per hour. Now I can use the formula power equals force times velocity. The force is the 6,801,5878. The velocity, remember we said we must convert this into meters per second by dividing by 3,6. That's why we're dividing here by 3,6 here to get this into meters per second. You could have just said 6,801,5878 times 20. Okay, same thing. And this gives you a total of 136,031,76 watts. So the power developed by the engine to maintain this constant speed of 72 kilometers per hour against the influence of the weight parallel and the frictional force is 136,031,76 watts. Okay. Now there's an alternative method where we can use the work done. We can say power equals work done over time. We need to get the total work done, and then we need to get the total time it takes to travel the 100 meters. Now, we know that the net work done in this case is going to be 0. Again, because of this idea of a constant speed, there's no change in the kinetic energy of the object. So delta EK must be 0. So which means also W net is also 0. Okay. So the work done by the frictional force plus work done by the engine equals 0. Now we already know what the frictional force is. We already know what the weight component, the component of the weight is. So now all we need to do is to say, well, let's find the work for these, for each of these forces. Now, in this example, The work done by gravity, remember in one of our videos, we spoke about 3 ways of calculating the work done by gravity. One of the ways we said was just to consider the vertical height, h. Once you consider the vertical height, h, you use the EP formula. So the work done by gravity is equal to EP equals mgh. Or if you're going to consider the length of the incline, you're going to say, well, the force that acts as the object moves is Fg parallel. You could also use work done equals Fg parallel times the delta x. In this case, the 100 meters. It should give you the same idea. Okay. So the work done by gravitational force can be either of these two. Guys, visit our video where we spoke about 3 ways of calculating the work done on an inclined plane. Okay. Now, so this will give me a total of what? I'm trying to calculate the work done by the engine force rather. So when I feed in all these numbers, I can see that the work done by the engine is 680,056,88 joules. Okay. Now I need to work out the time it takes for the object, for this combi to move 100 meters. Well, that's going to be simple because I already know that 72 kilometers per hour is 20 meters per second. So I can work out the time. How long does it take to travel 100 meters? If you're moving at 20 meters every second, it takes you 5 seconds. So the final step now will be to say the power equals the work done times time. Work done divided by time, which gives me 680,056,88 divided by 5. The power is 136,011,34 watts. Okay. All right, guys. This question looked a little bit long, but I'm sure at this stage don't lose it. Just do it step by step, okay, slowly, and eventually you get it. So power equals work done over time. See if you can work out the work done, see if you can get the time. Normally, if there's this idea of constant speed, you're more inclined to use power equals force times velocity. Okay. Let's look at our last question for this session. It says a crane with a power rating of 10 kilowatts lifts a weight of mass 500 kgs vertically upwards through a height of 10 meters from the ground at constant velocity. The frictional force that acts on the weight is 200 newtons. Calculate the following. Or they say calculate, then they're asking questions. So maybe this is out. So not, just says how long. Oh, yeah, maybe we are correct. Actually calculate. Calculate how long the crane will take to lift the weight if the crane operates at 90% efficiency, the speed at which the weight will rise. Okay, so now we're introducing another variable, 90% efficiency. So if something is 90% efficient, it means it's losing 10%. So 10% of that power is not available. That's what it simply means. Okay, but we'll discuss that now. Okay. So, if I had a free body diagram, this is what's happening. The crane is lifting the object up, and there are 2 forces opposing the motion of the crane: the gravitational force and the air friction. These 2 forces are balancing out the force of the crane. How do we know that they're balancing it out? Because we are told it's moving at constant velocity. So the word constant velocity, guys, means balanced forces. Okay. So we can calculate the force from the crane. Force of gravity plus force of friction. They're equal. Okay. So we are basically saying this should be the positive direction and this could be the negative direction. So the force of the crane is going in the positive direction. The other 2 forces in the negative direction. So now we can calculate the force from the crane. If we can calculate the force of the crane, we might as well calculate the work done by the crane. Remember, work done is force times distance. So all we're doing is we're multiplying throughout with the same distance. The same distance in this case is 10 meters. So if you multiply the force of the crane times 10, force of gravity times 10, force of friction times 10, then this statement also becomes true. Okay, so what will be the work done by the crane? It's going to be the work done by the gravity plus the work done against the frictional force. This gives me a total of 51,000 joules. So in lifting 500 kgs up, the crane has to overcome gravitational force and frictional force. It has to do work against those forces. Okay. So now I've got the work done. Okay. How long means time. I'm looking for the time. Okay. But now, before I go to the power equation, I'm told that the efficiency is 90%. Well, the percentage efficiency equals the power out divided by the power in. Okay, in other words, the power out is what the machine is giving. The power in is what is on the rating. So the power out is what we're going to get. We're going to get 90% of 10,000. 10 kilowatts means 10,000. 90% of 10,000 is 9,000 watts. So if the efficiency is 90%, it means we lose 10%. What's available is 90%. 0.9 in this case is the same as the 90%. Okay? So 90% of 10,000 is what we actually have. The machine is going to provide 9,000 watts. The 1,000 watts is lost to heat and sound. You know, most machines, when they're operating, they don't do it quietly. They make a lot of noise. Some of them get hot. And in that process, we're actually losing energy. So now we know the power and the work done. It's now easy. We've got the work done, 51,000. And we've got the power, 9,000 watts. So all we now need to do is to substitute into the formula. P equals W over T. And then we can get the time it takes. So power equals work done over time. We can now calculate the time. We get the time as 5.67 seconds. So this machine will take 5.67 seconds to lift the 500 kgs through that height. So the next question is the speed at which the weight will rise. Well, we've got distance, we've got time, so we can easily work out the speed. The speed is going to be distance over time. 10 over 5.67 is going to be 1.76 meters per second. So the 500 kg mass will rise at about 1.76 meters per second. Okay. Now, we could also use the formula that says power is equal to force times velocity. So we can actually calculate the force. The force of the crane is going to be the force of gravity plus the force of the air resistance. This gives us 5,100 newtons. So that is the force. If we use this formula, power equals force times velocity, we can get the speed at which the weight will rise at. Now, the output power, again, the formula for calculating the output power will be the same, 9,000 watts. The force is now 5,100. We can now easily work out the speed. So the speed is going to be 1.76 meters per second, which is what we got in the previous method. Once we get the speed is 1.76 and we've got the distance, we can work out the time it takes. Speed equals distance over time. 1.76 equals 10 over t. We can quickly work out the time equals 5.68 seconds. The difference is probably we rounded off. In the previous method, we got 5.67. Fair enough, our answers are quite comparable. Okay, guys. So when it comes to power, look out for keywords: constant force, constant velocity, okay, how long, and choose which type of equation you're going to use, how you're going to modify the power equation, okay, because basically power equals work done times time. So power equals work done times time. We just said P equals W over T. That is one of the standard format of the power equation. And then from there we said, well, you could extend this and say power equals work done over time, where the work done is actually delta E mech over delta T, depending on what you want to calculate. And then we also said you can also have power equals force times velocity. Okay, so depending on the way the question is worded, you can always modify the power equation. And sometimes you can also be asked to calculate the time. You can also be calculate the speed. All you have to do is to use the correct power equation, list down your variables, and see which power equation do you need to get what you want. It's been fun, guys. I hope I'll see you guys next time when we discuss, when we probably do more power calculations. This was an introduction.